As you've seen so far in this lesson, really this idea of implicit differentiation is using our derivative rules that we already know. It's just that if I differentiate a function of one variable with respect to another variable, the chain rule is what gives me this idea. We've been looking at it in terms of dy over dx, but we'll look at some other variables later on in this course. But all of our differentiation rules are still in play. And so let's look at how this idea of implicit differentiation kind of works in concert with some of these other rules. So we're going to work a couple of examples here. Let's consider the equation. And we're going to look at 4x cubed, this is going to be in parentheses, 4x cubed plus 3 times y squared equals x. And we want to find dy dx. In order to do that, I'm going to have to differentiate both sides with respect to x. So let's go ahead and show our notation of what I want to do. I want to differentiate this left side with respect to x. So I want to take the derivative of 4x cubed plus 3 times y squared. And I can do that to the left side as long as I also do it to the right side. Now then, obviously, the action is going to occur over here on the left side of this equation. This is the product of two functions. It is the product of 4x cubed plus 3 times y squared. So in order to take the derivative with respect to x of that product, I need to use the product rule. Now what the product rule says, you'll recall, is that it's the first function. So I'm going to start off with 4x cubed plus 3 times the derivative of the second function. So this is going to be times the derivative with respect to x of y squared plus the second function, y squared, times the derivative with respect to x of the first function, 4x cubed plus 3. And it all equals the derivative of x with respect to x. And remember, the rate of change of x with respect to x is simply equal to 1. Now then, I need to, and this is why your notation is so important, if I look here, I'm going to keep 4x cubed plus 3. The derivative with respect to x of y squared. Well, I take the derivative with respect to y, which is 2y, times the derivative of y with respect to x, which is dy dx. And that's what I'm ultimately going to want to solve for. So there's going to be some algebraic work to get that by itself. Over here, I still need to take the derivative with respect to x of 4x cubed plus 3. So this is plus y squared. Well, the derivative of 4x cubed plus 3 is going to be just simply 12x squared. Remember, if I'm differentiating with respect to x, I don't get this implicit differentiation step. And the derivative of 3 is 0. So there's the derivative with respect to x of 4x cubed plus 3. And this equals 1. So now I just need to get dy dx by itself. Let's go ahead and subtract this guy over here to the other side. If there's no dy dx there, then it needs to go to the other side. So I've got 4x cubed plus 3 times 2y dy dx equals 1 minus, and I'm going to go ahead and kind of multiply this out and call it 12x squared y squared. Hopefully you're comfortable with that simplification there. Well, now to get dy dx by itself, I just need to divide by this product right here. So I can say dy dx is equal to 1 minus 12x squared y squared all over 2y times 4x cubed plus 3. And I could distribute that if I wanted to, but for right now, we're going to go ahead and say that's the simplified version of this particular function. And here I've got the rate of change of y with respect to x. You'll notice it's described in terms of x and y, but that's okay, because I could take any point that was on this graph and find the rate of change of y with respect to x by plugging in my xy point into that expression right there. All right, let's take a look at one more. Let's take a look at the natural log of y squared, and we're going to say that that equals 4x squared plus 2x cubed minus 2. And again, I want to find dy dx. Well, that means I need to differentiate both sides with respect to x, so let's go ahead and start our notation process here. That is the derivative of the natural log of y squared with respect to x, and then I need to do the same operator to the right side. We'll take the derivative of 4x squared plus 2x cubed minus 2 with respect to x. All right, this has a lot of fun things going on the left side, because even before we do the implicit differentiation step, we need to think about what is the derivative of the natural log of something. And this is going to require us to use the chain rule. The derivative of the natural log of something is 1 over that something. So 1 over y squared times the derivative with respect to x of what that something is. That is the application of the chain rule when taking the derivative of the natural log of something. It's 1 over that something times the derivative of the something. That equals, over on the right side, derivative with respect to x. You'll notice this is a function of x, so I don't have to have this implicit step that'll end up happening when I look at the function of y. Derivative of 4x squared is 8x plus 2x cubed. Its derivative ends up being 6x squared. Now then, if I look at my notation, I need to take the derivative of y squared. So this is 1 over y squared times the derivative with respect to x of y squared is the derivative of y squared with respect to y, 2y, times my dy over dx. And it equals, so I'm going to go ahead and put our right side in descending order of powers there and call it 6x squared plus 8x. Now that if I look at the left side here, I can do a little bit of simplification. I can do 1 over y squared times 2 over y. This y can go into the y squared, and I can write this as 2 over y times dy dx equals 6x squared plus 8x. And now to get dy over dx by itself, I just want to multiply by the reciprocal of 2 over y. So if I multiply both of these sides of equations by y over 2, I get dy dx equals y times 6x squared plus 8x all over 2. So here on the left, you saw an example where the product rule can still work whenever we talk about functions of x and y. And over here, you see an example where we actually applied the chain rule as part of this taking the derivative of a function of y. And we ended up still with our dy dx once we took the derivative, in this case, of y squared. So all of the differentiation rules that we've learned so far are still in play, and we can use them in order to take this, to find dy over dx through this process we call implicit differentiation.